Hi everyone. So today we look at Norton equivalent circuits, and you should have looked at the Thevenin equivalent circuits already. If not, please go and look at that one before you look at the Norton equivalent circuits, because this lecture follows from that one. So by the end of today, you should be able to create Norton equivalent forms for resistive circuits comprising of independent, dependent, or both source types, just like you did with the Thevenin equivalent circuits. These are very similar types of forms, so if you're comfortable with the Thevenin equivalents, you should be comfortable with the Norton equivalents. So Norton's theorem is really the current analog of the Thevenin theorem. So you could take the whole network of resistors, but instead of using a voltage source in series with a resistance, here we form a current source in parallel with a resistance. And you'll see that we calculate these things in basically the same ways as before. In fact, the resistance here is, you can see it's still labeled as Thevenin because it is exactly the same thing you do. It is the same resistance that you find. So you don't need to do anything new to find it in this case. So it is formed basically the same way, the same procedures that we went through, except now instead of open circuiting the terminals and finding the open circuit voltage, we short circuit the terminals and find the short circuit current. So let's get started with the independent circuit, the independent sources only. So we have here the same circuit as before, and I'm going to remove RL here, and I will have this circuit now. So the first thing I want to do when I have this is find the resistance looking in, and I do this in exactly the same way as I did with the Thevenin equivalents. So I look in, and again we could redraw the circuit here, A, B, and then I look at this component and I see that this component is connected between A and B, and then this component is also connected between A and B. So I can see that they're in parallel. So now that I can see they're in parallel, I can find my equivalent resistance, which is 2.5 ohms. And to find the current, this is where it differs from the Thevenin equivalent. For the Thevenin equivalent, I would have open circuited these terminals. Now I short circuit them, and instead of finding the voltage, I find the current. Obviously the voltage across the short circuit is 0. So I'm going to use the theory of superposition again, and I will find, so this is 0 volts here. I want to find the current going down. So the current going down here is 10 over 5, which is 2 amps this way, plus 12 over 5, which is 2.4 amps this way. So they add up and they give me 4.4 amps into the short circuit. So now I could draw my Norton equivalent with 4.4 amps and 2.5 ohms, and that is how we form the Norton equivalent. For if I would like to solve the circuit, again, just like before, I connect my resistor to the terminals, and I'll find here this time, if I use the current divider equation, I will have the current going into this 5 ohm resistor is 2.5, which is this resistor here, over 7.5, the total resistance, multiplied by 4.4, which will give me 1.4667 amps, which is the same thing I got with the Thevenin equivalent. So you could see that whichever way I draw it, it is actually the same thing. Now, if I look at dependent sources only, this is exactly the same as the Thevenin equivalent circuit. Remember, for dependent sources only, the equivalent circuit is just the resistor. So I don't have to find a short circuit current or an open circuit voltage. I have to put in my source. If you remember the method we followed, you put in your 1 volt source and you find the current coming out of it, and that gives you the Thevenin equivalent resistance, the ratio of the voltage to the current. So if you can't remember, go back to your notes on the Thevenin equivalent circuit and review them. It is exactly the same. And for dependent and independent sources, this one also is the same. So the only difference is that now when we had the Thevenin equivalent, I used V open circuit here. Now for the Norton, I'm going to use I short circuit instead. But I still have to go through both calculations in order to get my Thevenin equivalent resistance. So let's look at the same example we did before, where we have, this is the same example from our Thevenin equivalent circuit. So I find the open circuit voltage here, and you could go through this again and you'll find the open circuit voltage is 3.75 volts. And then I find the short circuit current, and I find that to be 1.2 amps, and this is exactly what we did before. Now the difference is, when we're drawing the equivalent circuit, before what I did was I took the Thevenin equivalent voltage, which was 3.75 volts, and I drew it with the source in series with the resistor. This time I take the same resistance and I put it in parallel with the short circuit current of 1.2 amps. So you'll see there is some relationship between these two forms, and in fact we could switch between the Norton and Thevenin equivalents. The resistor is the same, so if I find my Thevenin equivalent, I could take that same resistor and I could put it in my Norton equivalent, and if I have the Thevenin voltage, I could find the Norton current through this equation. So if I have the Thevenin voltage, I could say I Norton is equal to V Thevenin on R Thevenin. Or if I have the Norton current, I could say V Thevenin is I Norton by R Thevenin, and I'll get the Thevenin voltage. So to summarize, you should be able to reduce circuits now to their Norton equivalent forms. And remember, they are essentially the same as the Thevenin equivalents, and we could convert between them, which you should also be able to do now. Next, we look at maximum power transfer. And for maximum power transfer, we need to know the Thevenin equivalents, because that is one of the determining things in the amount of power you could transfer.